In this video, I'm going to talk about forces and terminal velocity, and then move on to the ideas of energy and momentum. So the key things to understand about forces and terminal velocity are that the faster an object moves through a fluid, so that could be a liquid or a gas, the greater the frictional force. So that frictional force we usually talk about is drag or air resistance. So the faster it's going, the greater that actually becomes. So if an object is going really, really fast, it has more drag. If it's not moving at all, it actually has no drag. An object falling through a fluid will initially accelerate, so to begin with it accelerates, due to the force of gravity. So initially, gravity is greater than the force of air resistance, because there is no air resistance. So if I was to draw that out, so we generally say weight is the reason why it is. So to begin with, you've got an object here, you've got the weight acting down, you've got no forces acting up, so it accelerates down. That object will accelerate down. Eventually, the resultant force will become zero, and the object will move at terminal velocity. So over time, what actually happens is, because it's accelerating, as we said before, as it gets faster and faster and faster, the drag force increases or air resistance increases. So you can see there, it's getting bigger, and it keeps getting bigger until the point where weight and drag are the same size, and it no longer accelerates. It's going at a steady speed, it's going at a constant speed. We call that constant speed terminal velocity. So to go through it again, just to make sure you've got it 100%. Initially, only weight is acting on the object. Okay, there's no air resistance, it's not moving, so it accelerates down. After that, because it's accelerating, drag starts to kick in, but it's not balanced out with weight, so it still accelerates down, just not as much acceleration as before. And then they balance out, so it accelerates down very, very fast. Draw and interpret velocity time graphs for objects that reach terminal velocity, okay, including consideration of the forces acting on the object. Also, so I'll go through that in a second. Also, you need to calculate the weight of an object using the equation below. So the equation over here is very, very easy. Okay, so in terms of the graph, I'll just go through that. Okay, and the forces on the graph, if I number these, if I label these A, part B, part C, and if I just do a graph over here at the bottom, it looks like that. So it flattens out like that. That's part A, where there's no air resistance. That's part B, where there is some air resistance, and that's part C, where they're balanced. That's the velocity time graph. So you can see initially it accelerates, then it doesn't accelerate so much, so that's this part over here. That's part B essentially, and then over here there's no acceleration whatsoever. So that's over here, part C, where it's at steady speed. Right, forces and elasticity. So a force acting on an object requires a change in shape of an object. So just like we talked about forces causing an acceleration, a change in direction or velocity, they can also change the shape of an object. So if you've got a spring and you apply a mass on it, it changes the shape of the object. Force applied to elastic objects such as springs, as we've just been talking about, will cause it to stretch. Okay, cause it to stretch. And it should be to store energy. And store energy, that should be, there's a small little mistake over here. Cause it to stretch, result in the object stretching and storing energy. Bit missed off there, so it should be storing energy. So if you apply a force on an object like a spring, it will stretch and store energy. For an object that is able to recover its original shape, elastic potential energy is stored in the object. When work is done on the object to change its shape. So you've got a spring, if it's elastic, it will return back to its original shape. It will store elastic potential energy and then return to its original shape once that force is removed. The extension is directly proportional to the force applied. So remember, directly proportional, I've been banging on about that in assemblies I've done with you guys recently. When we talk about directly proportional, if you double the value on one axis, you double the value on other axes. If you divide a value on one axis by the other axis and you keep doing that in multiple places, you should end up with the same value. It should be a straight line through the origin. So it's F equals kx, okay? That's the idea for that. Right, so working energy is mainly equations, but one of the things I really need to push work done is the amount of energy that's actually transferred. So work done can be any form of energy. Work done could be kinetic energy that's turned into heat energy. Work done could be gravitational potential energy that's become kinetic energy. It can be any form of energy. So anytime a force is applied over a distance, work has been done. So there's your equation for it. like I just said, energy transferred is also work done, and work done often occurs against frictional forces. So when you're pushing against something, work is being done there too. If you divided work done by time, or divided energy transferred by time, that tells you the power. So the rate of work done, if you ever see that phrase, the rate of work done is power. Gravitational potential energy is the energy that an object has by virtue of its position in a gravitational field. So in other words, the higher an object is, the more gravitational potential energy it has. Kinetic energy is the energy an object has due to the fact it has a velocity, or the fact it's moving. Remember, it's a squared relationship. Remember, only the velocity is squared. Momentum is a sort of like a simplified version of kinetic energy. It's a property of moving objects. So momentum is equal to mass times by velocity. In a closed system, so that's no external forces, okay, the total momentum before an event is equal to the total momentum after an event. So we call that idea the conservation of momentum. The key thing there is it only works in a closed system. No external forces. Right, and that is our video on momentum. The only thing I really want to add a little bit in terms of momentum is that we do have crash forces sometimes, and when it comes to crash forces, you need to think about the idea of force is equal to change in momentum divided by time. So in other words, if you increase the time for a collision, you're decreasing the force that object feels. So that's how airbags work, okay? They increase the time for the same change in momentum, therefore they're decreasing the force. Right, so that's our video on momentum, energy, and terminal velocity finished.